Hello everyone, our new topic today is how to get the x distance to the point of maximum deflection for statically determined beam acted upon by uniform load. Before we have used the Newton-Raphson method to get the root of a curve that is intersecting at the x-axis. By using this method, first we introduce one point A apart from the y-axis by distance x0. Then we make slope at that point A. That slope will intersect with the x-axis at certain point, which will have a horizontal distance of x1. Then we will measure, or we will calculate the corresponding y or f of x1 for that point. Then we get point B. Second step is we are going to make slope at point B. Then this slope will hit again the x-axis at certain point. For that new point, we estimate the y value, and so on. We are taking several steps. That's why we are approaching to the root or to the zero y value. For this uniformly distributed load, for example, we have the curve of deflection, and this is a point of maximum deflection that have x maximum distance from the left support. Here, for that curvature, for the deflection, we don't have intersection with the deflection curve with the x-axis except for x equal to 0 or x equal to L. That's why we cannot directly use the Newton-Raphson method by that expression of x1 equal to x0 minus fx0 over f dash of x0. But luckily, we have the slope at the maximum point of deflection will be equal to 0. That's why we will move to the slope y dash, where we find that the point of 0 or the root point is apart by the same distance, which is x max from the left support. Accordingly, the Newton-Raphson method will be modified as we are going to see in the next slide. Before, the x1 was x0 minus fx0 over f dash x0, while we were dealing with y as a function of x. Now our root point is at another curve, which is y dash, which is a function of x. That's why we are going to replace the fx0 by f dash x0 and the f dash value by f double dash x0. The f double dash x0 is a curvature variation. These values are estimated by using the double integration method, where y double dash equal to m over ei, and y dash, the slope, is the integration of m over ei, while the y, the deflection variation, is given by again another integration of m over ei. Now let us see how we can proceed by using y dash slope curve. First, select the x0 distance, arbitrarily chosen. This is your start point. The slope from the left hand side is negative, so we will estimate the f dash x0 this time. We draw a curve, we draw slope at that point. Then we hit the y dash curve by another new point, which is apart x1, same like we have done earlier. For that x1, we are going to estimate the y dash of x1 point. For the f double dash of x0, we are going to go directly to the curve of y double dash, and for the corresponding x0, we will get f double dash x0. So the equation to be used is x1 equal to x naught minus f dash of x naught divided by f double dash of x naught. While for the modified Newton-Raphson method, we have xi plus 1 equal to xi minus f of xi f dash of xi divided over f dash of x prime all to the square minus f of x prime I prime multiplied by f double dash x I prime. For every item of this equation regarding f and f dash and f double dash will be changed and modified. For the f xi it will become f dash of xi, while for f dash of xi it will become f double dash of xi, and the square will be for the f double dash minus the f xi will be f dash of xi multiplied by f triple dash or d3y by dx square. How we are going to get the y triple dash? By recalling the expression that y double dash, which is a curvature variation, is equal to the m over ei. When you are going to make differentiation for dy double dash, accordingly you will make differentiation for m divided by ei. So for d3y over dx3 equal to dm over dx divided by y over ei. The expression, we are familiar with dm over dx, which is the shear diagram. That's why the y d3y over dx3 equal to q over ei. This is our new f d3y over dx3. The example we are going to use is we have uniformly triangular. We will have triangular load with maximum value B equal to 2 kilonewton per meter. The length of the support will be 6 meters, and the EI value 8 multiplied by 10 raised to the 4 kilonewton per meter run. The reason we are using the EI value is that we have to substitute in order to be able to use numerical method for evaluation. We recall the y double dash is 1 over ei multiplied by blx over 6 minus bx raised to the power 3 over 6l, as well as y dash and y as shown in the slides. Based on the calculation of double integration method, the x max lies apart from the y-axis by distance 0.519 L. In our case, it will be 3.114 since our span will be equal to 6. We are going to solve using Excel sheet, and we use arbitrary values, and according to the Newton-Raphson method, we are going to estimate the approximate x distance, and also we are going to try to use the modified Newton-Raphson. Thanks a lot, and see you in the next Excel sheet for the example solution.